one more minute. We wait for them to join. Okay, so let's look at the last one, the last question. So number 4, what is the horizontal displacement of the sphere from C? Okay, so taking the motion from point C all the way down to the ground here, there is a horizontal displacement. Why? Because there is a horizontal velocity. Okay, when at the instant when the ball started to fall, right, it has a horizontal velocity, means it's moving forward, right? It's moving forward. So we label it as the VC. Okay, VC, VX, meaning that the velocity in the x-axis. Okay, Vx, velocity in the x-axis, the horizontal velocity. So this Vx, as it falls, right, the trajectory of the falling trajectory, right, it is actually curved down. It's not straight down, it's curved down. Okay, this one we call the projectile motion. Okay, it's like a projectile, like a rainbow motion. Okay, so you have to know that the velocity in the x direction during a projectile fall, it will not change. Okay, so at any point when it is falling, right, at any point in time, the velocity of x is the same. Vx is the same. All right, so what is Vx actually? Vx is the velocity just before it fall, right? It is 1.5, right? Given in the question. So 1.5 here, 1.5 ms minus 1. Okay, so during the fall, the horizontal velocity will be maintained at 1.5 ms minus 1, 1.5 ms minus 1. Okay, now to calculate the horizontal displacement, how do you calculate this one? How far can you go when you are moving at 1.5 speed, okay, and you fall down, it's falling. Okay, so this one we call it dx lah, distance x. Okay, so to calculate the horizontal displacement, we use the formula, the same formula. Okay, we use the same formula, s equals to ut plus at squared, half at squared. Okay, ut plus half at squared. Now, acceleration, is there any acceleration? We are only considering the horizontal movement. Okay, now the velocity, the horizontal velocity has nothing to do with the vertical velocity. Okay, 之前我们做的那种 equation of motion 就很像比如说一个高山，然后we consider the vertical motion, right, falling down, right? 为什么我们一来用的 initial velocity 是 u 等于0 before 它跌的时候，那个我们是 assuming the velocity is the vertical velocity. Okay, u 等于0，那个是 vertical velocity. Okay, because we are only considering all the motion in the y-axis, and we are not looking at the x-axis, and it has nothing to do with the x-axis. Why? Because the y-axis is perpendicular to the x-axis, so it has no relation. It's like perpendicular, right? No relation. Okay, so in this case, we are considering only the horizontal direction, the x-axis. So we are not looking at the vertical velocity. Okay, so which is why the initial velocity Vx 就是这个 u 这个 u 是 1.5 ms 减1，也就是我的 Vx， 明白吗 ？Okay, so maybe some of you ask， okay, 为什么 u 不是0？因为它刚刚要跌，为什么不是0？因为之前我们做的那个0，那个是 vertical velocity。Okay, so 这个是 horizontal velocity， meaning that before it falls, it is moving at 1.5 ms minus 1. Okay, now acceleration, there's no acceleration. Acceleration is equals to 0, 因为 Vx 都是 constant, 对不对？ Vx is the same 1.5, 1.5, so it's constant. So acceleration is 0. So since acceleration is 0, we cancel out this one. Okay, so only s equals to ut. So u is 1.5. T is what? T is the time taken for the ball to fall, right? Time taken for the ball to fall is the one that you calculated in number 3. T 等于多少？刚才我们算到0.54秒。Okay, so times 0.54 seconds. And this time, the time taken to fall down is the same, regardless you're moving in a horizontal or vertical. The time taken to fall down is the same. So we can just use 0.54. Okay, so 1.5 times 0.54, then we get the horizontal displacement is 0.81 meter. Okay, so this is how we calculate the horizontal displacement. Okay, so that you know when you are moving at a certain speed, how far can you go in the horizontal distance when you are falling? Okay, how far can you reach? Okay, so this is important, especially when for all the 如果你要比如说你站在那个山上面，你要跳下那个水 ，of course 你要知道你要跑几快，你要跳不要跳过，一定要跳过那种如果下面有那种石头啊什么 ，of course you don't want to fall on the rock, right? Of course, so you want to make sure that you have enough speed that you can reach the horizontal distance that is further away from the rocky ground. Okay. Okay, 2 minutes to wrap up everything. This one, if you want to copy down, you can copy down the solution, and then I will go to, I will continue the lesson just a little bit. It's not many. I want to finish the forces and pressure. So today I will talk about the Bernoulli's principle, which is the last part of chapter 3, the force and pressure. Okay, it's not many, that one, because that one has no calculation. That one is just concept. Okay, so after I finish that one, and then I will spend the time together with you guys to do some exercises to practice the exercises. Okay. Okay, I will be back in 1 minute. Okay, let's continue. So if you have, so just bring this up. Okay, so Bernoulli's principle. 之前我们学Pascal is about pressure, the hydraulic system in your car brake system, the aeroplane brake system, all that. They use the Pascal principle, right? And then after that, 我们也是讲 Archimedes. Archimedes principle is about buoyancy. Okay, about density, about buoyancy, whether object floats on the sea and something like that. Now we come to the Bernoulli's principle. Okay, now Bernoulli's principle is also about pressure, but pressure of a moving air. Okay, pressure of a moving air or a moving fluid. It can be liquid or air lah. Okay, now here, let's look at the first diagram. So here you see a pipe. Okay, let's say this is a pipe. Okay, a water pipe. Now, how does the water flow in the pipe here? Okay, you see the cross section is different area, right? Each section is different in terms of the cross section area. Okay, so this is bigger, and then it constrict down to small fine tube, and then it expand again. So how does this really affect the water flow? Just think about it. Just think about it. No need to answer me or anything. Okay, imagine there are water flowing in here. So from left to right, how does the flow behave? How does the flow behave? And what is the relationship between the flow and the pressure? How does the pressure change? What is the speed of the flow? How does it change? Okay, so today we are going to learn all about all this. Now, let's imagine, okay, let's imagine here we take one single particle, the motion of one single particle. Okay, now, initially in this chamber, it is moving at a certain velocity. I label it as V1. V1, so it's moving at V1. Now, as it enters this section, this constricted section here, you notice that the particle is moving faster, V2. And then V2 is bigger than V1. Okay? And as it continues to flow forward and enters this narrow section, the velocity will increase further. Okay? So V3, if you write V3, you actually see that V3 is bigger than V2 and V1. It will speed up. Okay? So the flow will speed up. And what happened is at this opening here, so it going from the small cross-sectional area enters the bigger one here, and then the velocity will come back and slow down again, becomes V2. And then eventually it will decrease again, becomes V1. So this shows how does the speed change in this constricting the narrow water pipe. Now we are going to talk about why. Why does this happen? Okay. Now, this has something to do with the Bernoulli's principle. Now, before I talk about why, you have to understand what is the meaning of volume flow rate. Okay, volume flow rate. Now, let me take an example. Okay, volume flow rate. Okay, let's look at this one, the pipe down here, the second pipe. Okay, now imagine this is a water pipe and this is the opening. Okay, this is the opening. So let's say we take a stopwatch, okay, and when the water flow here, and it reaches the opening, let's take at that particular instant of time, t equals to 0 second. Okay, t equals to 0 second is when the water is reaching the opening, not coming out of the pipe yet, not coming out yet. Okay, imagine this is a hose, something like that. Okay, now t equals to 0. Now we start the stopwatch. From 0 to 1 second, t equals to 1. How what is the amount of water flowing out in that 1 second? Okay, so from here, let me draw it. Let's say this is the water flowing out like this. The dotted line is the water, like this. Okay, so let's take this is volume 1, V1. Okay, so there is of course there's a certain volume of water flowing out from the opening, okay, in this 1 second. Now, volume flow rate is the amount of water flowing in 1 second, and it is measured in volume. Okay, it is measured in volume. I repeat, volume flow rate is the amount of water in terms of volume flowing in 1 second, just like this one. So in 1 second, this certain amount of water flowing out of the hose. Okay, so it's like another way to measure the speed. Okay, it's another way to measure speed. Now, so volume flow rate, there is a principle saying that the volume flow rate is constant in the pipe. Okay, whatever pipe is it, whatever type of pipe, the volume flow rate must be constant. Okay, so meaning that if this amount of water flowing out in 1 second, at any point, it must be maintained this amount of water flowing in 1 second. Okay, now let me go back to the tube just now, the first one, the first tube. Okay, now why does the velocity increase? Let's start with the volume flow rate. Let's say at t equals to 0, the water is at the here, it's at here, is about to enter the tube. Okay, and at t equals to 1, the water enters the tube and then it reaches here. So I shade here, this is the water. Okay, just imagine. Okay, and this is the line of separation over here. This is the line, the boundary. Okay, the boundary. Now, in 1 second, this amount of water entered the tube. Let's label it as V1. Okay, this amount of volume enters the tube. Now, what happens in the next second? In the next second, all this water must pass through this red line. Okay, all this, I repeat, in the next second, all this water that enters the tube, it must make it past the red line. Why? Because they have to maintain the same volume flow rate. Okay, it has to be this amount of volume of water flowing in the next 1 second. Okay, now what happened is, since the next section here is constricting, it is reducing in volume. Of course, it's obvious that this chamber is has less volume than the previous chamber, is smaller, right? Now, what happened is that all the water is not going to fit in this smaller chamber, of course, right? So since they want to maintain the same volume flow rate, and one important point is that water cannot be compressed. Okay, previously we talked about water is incompressible, right? You cannot compress water, but you can compress gas, right? So if you cannot compress water, and water has to maintain the same flow rate, they have to make it past the red line in just 1 second, even though the next chamber has a smaller volume. Okay, they have to somehow think of a way to make it past the red line. Okay, and since they cannot be compressed, the only way to make it past the red line is for them to increase their speed. Understand? Okay, I repeat, since they want to maintain the same volume flow rate, this amount of water has to make it past the red line in the next 1 second. Okay, the only way for them to make it pass is to increase their speed. Okay, is to increase their speed. So in the second chamber here, V, okay, speed, speed will increase. Okay, in this chamber here. So what happened as it flows inside this even smaller tube, the center? Of course, the speed will increase even more. It will increase even more. It will go faster and faster. So water flows faster at the narrow section, okay, at the middle section, Now, don't confuse speed and volume flow rate. They are a little bit, they are different. They are different. They are both a measure of speed, of course, but there is a subtle difference between them. Speed and volume flow rate is different thing, two different things. Okay. Now, so in conclusion, here we know that as the cross section of the tube decrease, cross sectional area of the tube decrease, the flow speed will increase. Okay, so the flow speed will increase. Now, how does that affect the pressure? How does that affect the pressure? So in Bernoulli's principle, remember that as the speed increase, okay, as the flow speed increases, it can be gas or it can be water, any type of fluid. As the flow speed increases, the pressure decreases. This is what Bernoulli is talking about. Okay, just simple one statement. When the velocity increases, the pressure decreases, and vice versa. Okay, meaning that at center here, you have the lowest pressure. Okay, the center here, this one. And this one, these two, of course, here at the left and right end is higher pressure here, and also higher pressure here. Okay, now let's look at the next tube. This one. Yeah, this one. Okay, everybody look at this, the bottom, the diagram at the bottom here. Now this one is also the same tube. You see that the cross section is decreasing, right? Okay, so this one is, okay, this type of tube, varying in the cross section, we call it the Venturi. Okay, the Venturi tube. And the effect of the tube causing the increase in the flow speed, we call it the Venturi effect. Okay, Venturi effect. Now, what happened is when water flows inside this tube, okay, here flows right here, and here it will speed up, right? Speed up, and then it will slow back down. Okay, slow down. So middle is highest velocity. Now, highest velocity, highest pressure, correct? Sorry, lower pressure, right? Correct? Higher velocity, lower pressure. So at the middle, if you compare the water level, you will see that the middle, the water level is lower than the water level at the left and at the right, like this. Okay, why? Because there is a atmospheric pressure pressing down here. Atmospheric pressure pressing down here, and down here, right? ATM. Now, since here the pressure is lower than point A and point B, so you will see that the water level is a little bit lower, okay, because it is lower compared to pressure A and pressure B. So pressure A and pressure B has a higher pressure, so it is able to push the water level more higher up in the scale. Understand? Okay, so this is what you will see. This is we call the Venturi effect. Okay, so you see different water level because of the varying pressure in the tube. Okay, now if we use a normal tube, let's say we use a normal tube like this one. Okay, let me just draw it out. Let's say, okay, like this. If the cross-sectional area is the same, compare the pressure at A, B, C. If the water is flowing from left to right, this is the water flow. Okay, what can you observe the water level in these three tubes? Is it going to be the same height? Or is it going to be decreasing? Or is it going to be increasing? Okay, now remember that generally in a water flow, water flows from high pressure region to a low pressure region. Okay, so meaning that if the flow is coming from the left to right, then the pressure at the left region should be higher than the pressure at the right. Okay, so pressure here, PA, sorry, is higher than the pressure here, PB, and is higher than the pressure at C here. So what happened is you will see that the mark and the water level should be like this. Highest, because pressure at A is the highest, right? So it pushes the water level up a bit. So this is the highest, and then followed by the water level at B is a little bit lower. Okay, and the water level at C is the lowest. Okay, now if you apply this into the venturi tube just now on top, this one. Okay, let's see. So A, B, C. Pressure at A is higher than pressure at B, at C. Pressure at A is higher than pressure at C because water is flowing from left to right. Okay, and water flows in high pressure region to low pressure region. So of course, the water level at A must be higher than C. Okay, like this. Now, if you combine with the venturi effect, pressure at B, it should be the lowest. Okay, even though it is before C, but it should be the lowest. Why? Because of the increase in the flow speed. Okay, so what you will see is the water level at B is the lowest, like this. So this is the idea. Technically, it should be like this. Okay, this is the highest, A, followed by C, and then the lowest is B. Okay， 明白啊？为什么最低？因为这个atmospheric pressure pressing down here, and the pressure of this region is lowest. Okay, so lowest, then the water level should be lower because of the higher difference between the atmospheric pressure and the pressure at the inside the water. Okay, so this is we call the venturi tube. Now, Bernoulli's principle is talking about this one. Bernoulli's principle is talking about, let me just write this down. Okay, so Bernoulli's principle states that where the speed of fluid is high, the pressure is low, and where the speed is low, the pressure is high. And this not only applies to fluid, this not only applies to water, it also applies to gases. OK， 所以你会发觉到好像你 let's say 你在车里面你驾车很快，是如果你开窗的话，you will feel that 你车里面的东西很容易飞出去。为什么？因为你的窗外面是那个 there's a velocity of the air is flowing, right? It's flowing fast. So the region outside of your window is lower pressure, has lower pressure compared to the air inside your car. Okay, so which is why 你的东西很容易飞出去，因为 there's a pressure difference between that. Okay, and you see this Bernoulli's principle everywhere. You see this everywhere. For example, in the airplane. In airplane, now let's talk about the airplane. How does Bernoulli's principle happen in airplane? Okay, let me just take this. Okay, so if you take the wing of the airplane, let's say this is the airplane, and this is the wing, right? Yeah, something like this lah. Okay, now what happened is, let's say you cut here. You cut from the top. Okay, you cut from the top, and then you take off this piece, and then you look from the side. What you will see is the cross-sectional area of the wing. Okay, you cut out this one, you take out the piece, and then you look from the side. You will see the cross section of the wing, and it looks like this. This one we call the airfoil. Okay, now how does the wing fly? It uses the principle of Bernoulli's principle. Okay, now let's say this is the airfoil, right? So the plane is moving, so it's during takeoff it increases its speed, right? Increases its speed, so it's moving to the left. Let's say it's moving to the left. Okay, now it's moving to the left, so airflow is coming from the left to the right, correct? This is the airflow. Now what happened is this airfoil, why it is designed in this shape? Why it is designed in this shape? Because you see at the in front, this point, the nose, we call the nose. The nose here, it separates the air into two layers. Okay, some of the portion of the air will go on top, and some of the portion of the air will go below, like this. It separates into two regions. Okay, now let's zoom in one single particle of the air at the top. Okay, let's say this is one particle at the top, and this is another particle down here. Okay, particle A and particle B. Okay, now the concept behind it is both these particles, they have to reach the tail, this point, let's say point B. They have to reach point B at the same time. Regardless, like no excuse, they have to reach point B at the same time. There's a principle saying that. Okay, so what happened is you will see that why on top is curved, because on top, since on top is curved, right? So on the distance traveled by particle A is further than the distance traveled by particle B. Okay, because on top the curved section is longer. Okay, so particle A has to cover more distance, longer distance than particle B. So what happened is that since particle A has to move longer distance, and both of them has to reach the same time, meaning that A has to move faster. Okay, so particle A has to move faster because it has to cover more distance and they have to reach at the same time. So what happened is that the layer, the air above this one, on top, the layer above, faster flow speed. The air above the airfoil moves at a faster speed, and the air below the airfoil, it moves at a slower speed. Okay, now what happened here? Can you apply the Bernoulli's principle? Since the air above the airfoil moves at faster speed, so on top it creates a low pressure region, right? So here is, okay, let me use a different color. On top here, it creates a low pressure region because the flow speed is faster according to Bernoulli's principle. Here is low pressure region, and below is high pressure region. Okay, so there is a pressure difference here, a pressure differential here. Now what happened as a result is there is a resultant force acting from the bottom, acting upward. Okay, because resultant force acts from the high pressure region to low pressure region. Okay, and this resultant force is, we call the lift. And this is how the airplanes fly. Okay, so you see how they use the concept of Bernoulli's principle. So it all starts with the design of the airfoil. They design airfoil so that on top is longer than the below, so that air has to speed up on top. Okay, and as it speed up, it creates a low pressure region, and the high pressure region at the bottom will create a resultant force that acts upward. Okay, and sometimes even you will see that the wing, right, this is the airfoil, right, it will increase the length of the airfoil. It's like this is the wing, and this is the airfoil. Before takeoff, if you're on a plane, you see the wing, just before takeoff, they will increase their length here. It's like we call the flap or something like that. They increase this one just before takeoff. Why they increase this one? because they want to make sure the pressure difference is, they want to increase the pressure difference. Because if they extend this one outward, the distance of this one on top is even longer. Okay, it's even longer compared to the distance below, so that they are able to create more pressure difference and they can increase the lift. Okay, so what happened is they increase the lift so that they can move at slower speed to be able to take off. Okay, if they don't extend this one, what happened is that they need to reach higher speed, the takeoff speed. Okay, I write it V takeoff lah. Okay, they need to reach a very high takeoff speed to be able to take off. So if your takeoff speed is very high, then you need to extend your runway, right? If your takeoff speed is very high, then you need to extend your runway. So one way to do it is to design this one, extend this one, the flap, so that I can further reduce the takeoff speed, and I can take a shorter distance to take off. Okay. Now, okay, I still got still got 2 minutes. Okay. So from here, so this is one principle, one application of the Bernoulli's principle, and another application would be the Magnus force. Okay, now I want to talk about the Magnus force. Okay, let's log out and log back in first, because left 2 minutes I don't have enough time to talk. Let's rejoin back the meeting.